Hello and welcome to Lecture 15, Part 1 for Life in the Universe. In this lecture, we're going to start Unit F on telescopes and spacecraft. This is our last remaining unit, but will take more than 2 lectures to do. We'll need 3 for it. And we're going to start learning about telescopes in just a moment. But this being the first video of the lecture, I've got an alien for you, and that's one of the bugs from the 1997 movie Starship Troopers, kind of loosely based on a novel by Robert A. Heinlein. Um, I guess it's rather common in science fiction to have insect-like aliens. Nothing actually alien about insects, more of them than there are of us on Earth, but I guess we still react that way to them. Um, I originally didn't really care for this movie very much. I thought it was kind of silly, and then I realized that it's intended as a satire and a parody. And once you understand that, it's a great movie because it is a great parody. And also, the more than 20-year-old CGI holds up quite well, and I think that's because they understood what they could actually do with the technology and what they couldn't, and they didn't try and do things they couldn't. Anyway, I'll have a link in the description for music from the soundtrack if you want to go listen to it. And there's a really awesome version, though, that you can find on your own, doing the soundtrack on an accordion. All right, so this unit is about the literal tools for studying the universe. We'll mostly look at telescopes, but at the end of the unit, we'll take a look at spacecraft exploration of the solar system. Now, within the solar system, it is possible with some significant expense and effort to go look at things up close, usually by robotic spacecraft. So far, we've only gone to near Earth orbit and the moon personally, but maybe in the not too distant future, we'll go a bit further. But except for within the solar system, and even for a lot of what is in the solar system, most of what we know, if not all of what we know about that part of the universe, comes from our ability to collect and analyze the light from those distant objects. And for that reason, the telescope, being how you collect that light, is, I think, no doubt the most important thing technically that has ever happened in the history of astronomy. Now, I suspect the type of telescope that you're most likely familiar with is what we call a refracting telescope or a refractor. That is a telescope that uses lenses to focus the light. And before we get into telescopes, let me say a bit about the phenomenon of refraction. This is what occurs when light goes from one material to another. Say, for example, you've got light in air. Turn the pen on here. And then it goes into glass. All right. Unless that light hits the boundary exactly perpendicular, which the little curve I just drew didn't do, to the surface, it's going to change direction when it hits that surface. And how much it changes direction depends on some properties of those materials we call the index of refraction. And so depending on how the indices of refraction those materials relate, that'll determine how much things bend. And to use this to focus a light, the idea, of course, is you take a lens and you shape that lens such that it will focus the light where you want it. Now, if we're meeting in person, I'd have a really cool demo like the one on the left to show you, but we're not, so I'll just use the little animation there. And I know that although when I'm looking at it on my computer screen, these animated GIFs run at normal speed, they're a little slow in the video, but I think it will be fine for you. Anyway, it turns out that Pyrex, it's actually now a name brand, but more technically it refers to a particular type of borosilicate glass. But that Pyrex glass and soybean oil have almost the same index of refraction. And that means that light doesn't change direction very much when it goes from one to the other. And what's being shown in that demo on the left is a beaker of Pyrex is being submerged into soybean oil, a small beaker into the larger beaker. And initially you can see the small beaker because there's air in it, so you do get a change of direction when the light goes from the Pyrex into the air inside it. But as the air escapes and it fills with soybean oil, there's very little change of the direction. It becomes really hard to see. On the right, you have something that's actually kind of creepy. It's an aerogel that has an index of refraction that is quite close to the index of refraction of air. It's not perfectly transparent. Light does scatter a little bit in it, which is why you can see how where it is, but it has that kind of ghostly appearance to it because the light is not changing direction very much when it goes from the air into the aerogel and then back from the aerogel into the air. All right, now for astronomical purposes, this is the most common arrangement of a refracting telescope. Looking at something way off to the left somewhere, so far away that the light from that distant object from the left is basically coming in parallel. Now, the first lens that the light will encounter will be the largest lens in the telescope, which we call the objective lens. Whenever we talk about the size of a telescope, if it's a refractor, we mean the diameter of the objective lens. If it's a reflecting telescope, which we'll talk about in the next lecture, it will be the diameter of the primary mirror. Anyway, light comes in, hits the primary, which an astronomical refractor is most tightly focused somewhere before the light gets to the second lens called the eyepiece. And the eyepiece makes the light coming out of a telescope parallel again as it goes into your eye. The optics of your eye would focus that on your retina. Now, here's one thing to notice about this arrangement. Note, let's follow this light ray that comes in the top of the telescope here. Note if we follow that light ray, and I'm not that good at drawing a straight line by freehand here, note that that light ray comes out of the telescope at the bottom. So astronomical refractors typically give us an inverted image, one that's upside down. And I can demonstrate that here for you with just showing an inverted image with a lens, just with this little magnifier here. But if I hold it, say, right here, and you look at the image of the top of my head from the light that's gone through that lens, you see I'm upside down in the lens. And there's my beard down there. There's the top of my head. Now, for telescopes that we're using to look at things on the ground, this is not the arrangement we want, and you have a different arrangement of the lenses so that you get a right side up image. Although presumably deer would probably like it if the telescopes on deer rifles worked like an astronomical telescope, because the upside down image of the deer would make it a lot harder to hit. But for an astronomical telescope, which way is the top, which way is the bottom is arbitrary, so you can do it pretty much either way. All right, so this little video is going to be relatively short. The others are going to be a little longer for this lecture. So here's our secret code. Kyle Cudworth was my PhD advisor in grad school. And this is a picture of a blackboard from his office. Now, I started graduate school in the fall of 1987. In the following summer of 1988, I started working with Kyle on a summer research project. And this equation that he wrote on the board at that time, along with this stuff up here as well, had to do with the project I was going to be doing that summer. And when I realized that he wasn't erasing it, I developed a goal to graduate before he erased it. Well, it turns out that blackboard is in a different office in the observatory now. It's since been moved, but that equation is still on it. Something he wrote there in summer of 1988, and it's still there, and I'm recording this in early October 2020. So I definitely succeeded in graduating before he erased it, and my goal now is to retire before he erases it. And given that it's been there for, what is that now, 32 years, and I've got a little bit less than 11 years now before I can retire in my full pension. I think I've got a decent chance of making it. So anyway, Kyle's Blackboard is our code for this video. And in the next video in this lecture, we'll talk about what actually detects the light after it goes through the telescope. So I'll go record that one after Zoom processes this one.